Good morning, everybody. My name is Bertrand ARDOUIN. I'm working with XMOD technologies. I can be here today in Hereford to present you this slide. So I make an experiment, try to use the voice recorder so that you have a relatively live feeling about this the slides. So let us start with this discussion about practical implementation of reliability-aware compact models in simulation software environments. Let's go on. Slide 2. This is the outline of this presentation. So after presenting briefly the context and an introduction, I will discuss about the proposed transistor aging model and its Verilog A implementation into the ICANN standard model. And then we will arrive to the most important part of the slides, which is the practical implementation of this model in the simulation environment. And then I will give a short conclusions. Okay, slide 3. So the context of this work is indium phosphide HBTs. So this is 3.5 technology. But this general principles works also for SiGe HBT, MOS devices, and probably also other technologies. So we are talking about also a dynamic aging model. This is important because this is basically an aging model which works also for switching mode or large signal behavior. But the practical implementation itself also would work in the same way for a static aging model. Okay, slide 4. So let us start with this introduction. So the question is how to implement an aging model in a CAD environment. So the easy way would be to add simply a new parameter age in the cadence CDF parameters. For instance, a new pixel variable. That would be nice to have that features, but the problem is that it's not possible because the transistor age or degradation depends on the temperature, on the voltage in a dynamic manner, and also on the time. So the stress or the aging has to be simulated for each circuit because each transistor instance suffers a different stress and degradation, and it's not possible to determine a priori the aging of a device. So we need to calculate this aging for every transistor. So why not simply adding a calculator tool as a post-process before the simulation? And this would yield a degradation as a function of time, voltage, temperature, and device geometry. And it's not possible actually because the aging is a dynamic phenomenon. It does not depend on the quiescent bias point, but on the integration of a voltage impact over time. So let us have a look at this figure here in slide 5, where we have the collector, arbitrary collector emitter voltage of a transistor as the function of time. The red line is basically the limit voltage for which you have a hot carrier degradation. And the green line is the DC operating point. And basically, this bias point is below the limit. So in principle, it predicts no degradation. But for a large signal arbitrary value with arbitrary value, you see that the voltage can quickly raise above this limit from times to times. And then the degradation occurs dynamically. And this is why a dynamic model is important, because it's the only way to take into account the degradation over time and to integrate it during the circuit lifetime. Okay, so slide 6. So I'm going to present now our proposed transistor aging model. So we start by two figures on the right where we have the HBT gamma characteristics monitoring during a stress campaign. And we see that over time we have some changes in the currents. We have a moderate IC increase, then a decrease at higher currents. We also have an important base current increase. And overall, this ends up with a global current gain degradation versus the stress time. So this is the situation we have typically in this kind of aging campaigns. So if we have a look at on the physics-based sides, we might find that the mechanism responsible for the degradations are donor traps at the emitter-base junction surface, and they are responsible for this current increase. So the trap concentration increases linearly with the stress time, and the increase rates depends on the bias. So this is what can be obtained during an analysis of the degradation mechanisms. So the point is that donor traps, I'm now on slide 8, the donor traps are not actual model parameters. If we look at the HICAM model, for instance, we have an equation for the transfer current or collector current and for the base current. And in these equations, we don't have any such parameter like donor traps. We have saturation currents, for instance, IS or IBEIS. So the lucky strike is that those saturation parameters follow the same linear evolution as traps with stress time. So basically, these saturation current parameters can be advantageously used as variables for the aging model. And this is what we are going to do now. So let's go to slide 9. So this IBEIS and IS are modeled according to a generation mechanism. So that means that we have differential equations to model them with a constant increasing rates which follow an Arrhenius law. And this means that now the model parameters IBEIS and IS are not constant anymore. They are varying quantities, and they are described by this Arrhenius law with 4 new parameters, activation, energies, and coefficients. And for more details, you are invited to refer to the reference paper here below on slide 9. So how do we implement that into the standard HICAM model? Well, that's not very difficult because we basically have the Verilog A code for the standard model, and we just need to add a few modifications to do that. And you see here on slide 10 that on the left you have the standard equivalent circuit for the HICAM model, and on the right the modified elements, where we had 2 new nodes accounting for the variations of IBEIS and IS. And you see the used lumped elements, which are basically responsible for implementing the differential equation here. That's fairly simple. A current source and a capacitance, and that's basically all the things we need. So let's go to slide 11, where we have the real modifications of the code in red. So you see on the top, on the first block, that we have defined two new output nodes, internal nodes for the transistors. We have now the parameters in the second block, IB, IS, and IS, which are now dependent from initial values and also the voltage of the 2 new nodes. Then the third block is basically the implementation of the Arrhenius law. And finally, in the last block, you have the branch equations actually implementing the differential equation. So that's fairly easy to have this in the model. The only thing to remember is that now we have 2 new output nodes which account for the degradation. So let us talk about the most important part now, and which is the practical implementation. We are on slide 12. you have here sketched the basic simulation flow, where we start on the top left by the circuit setup and the stimulus definition, typically in Cadence software, where you just put your various elements. And the software then generates a netlist, which is passed on to the simulator, and the simulator gives electrical characteristics that you can again display in the graphical environment. This is interesting, but the point is that this is more or less a black box, and it's very difficult to interfere in this simulation flow. So the point is, one of the easiest way to interfere with the simulation flow is to go to the an extra part, which is in the netlist, the reference to the model library from the foundry. What we can do is to break this reference to the model library and add a clone of this library with modified model, integrating the new aging laws. So by doing this, we can basically enter the simulation flow by breaking the reference to the model libraries. So how can we do that? Let's go to slide 13. By changing the reference model files in Cadence, it's very easy. You just need to go to the setup and model libraries, and then you can add a different root model file. And this root model file will point to your modified libraries, and that's it. So basically, the generated netlist will still refer to the primitive model names. So that means, in other words, that the simulator thinks that it is still using the foundry models. But the new model files are used instead. So this means that the standard simulation flow is not affected, but the simulation is now based on the new model libraries. And this is the way we can do that. Let's go to slide 14. So what can we do with this trick? Well, step one, what we can do is to run the initial aging simulation of the circuit to calculate the amount of degradation for each transistor. And the step two is to run simulations with post-stress models. Actually, one specific model for each transistor instance. So let us review these two different steps. Let's go to slide 15. So step one, the initial aging simulations. We again have the simulation flow, which is in principle integrated into the simulation environment. So in our case, in this case where we have studied the proof of concept, it has been done manually, but it could be easily automated. And what we are doing is that, what I mean by manually is that we use the command line. So the first step is to export the netlist from AD, from Cadence. Then we simulate this netlist in the command line mode. And then we get the standard SPICE output file. And we post-process the results basically here with a Perl script. So let's go to slide 16. So just as a quick note, here we make reference to ADS. This is just basically because we have used HP SoftSim instead of Spectre, Cadence Spectre. But that's basically a very similar principle. Here we use the Spectre syntax as much as we can, so that there is basically no difficulties doing this with another simulator. So we basically run the simulator in command line. We specify the input netlist and the output file. Again, the netlist refers to the modified library with the aging models, and we get the raw results in the output file. You have here on the right hand side of the slide the structures of the output file, which is basically here the header, where you have a definition of all the variables in the subsequent time steps of the simulations. And you see that you have a number of instances and sub-circuit instances, and then also various nodes. And this means that in the output file we have a specific voltage node for every transistor instance, which keeps tracks of the variations of the degradation parameters. So all the information we need is basically stored in this output file here. So how can we access this information? Let's go to slide 17. So just to summarize again what we are going to get from this output file, from this transient simulation, is that we will have the amount of degradation for every instance in a given circuit. For instance, now you can see what is the degradation, or which are the transistors which are the most sensitive to the degradation in a given circuit. And that's the kind of information that is stored in this output file and that we want to automatically retrieve now. Let's go to slide 18. So for this we have a specific script which will post-process the information from the output raw file. And this script will retrieve all the information that we need and stores it automatically in a so-called aging file. We can do that for various time steps. We can do that at any time step of the transient simulation. Just a specific note here. We have simulation times which are in the range of nanoseconds, but we have defined in our simulation some accelerating factors so that this simulation times actually corresponds to years of aging, so that we have a clear correspondence between the simulation time and the aging time. But in a more compact form, because of course we cannot afford to run the simulators for 10 years. Okay, slide 19. So now the aging information is instance specific. That means that we have a different aging for every transistor. This is what we have seen in the previous slides. So therefore, modifying the model libraries is not really practical, because this would require as many models as instances in the circuit. And this would increase dramatically the model library structure. You can imagine that you need as many directories as you have instance of transistors. So if you have a circuit with 1,000 transistors, then you need 1,000 duplications of the library. That's really not something we don't want. And this would require also that every instance in the circuit call a different specific model, which causes other issues, because we don't have very simple ways to modify the netlist in the simulation flow, and we don't want that. So the preferred option is to use alter statements. Alter statements are specific commands to the simulators, which allows you to change the value of any modifiable component or netlist parameters for any analysis that follows. So the parameters to be altered can be a circuit temperature, a device instance parameters, a device model parameters. This is what we are interested in. A netlist parameter, or a sub-circuit parameter for a particular sub-circuit instance. So that's exactly what we want. We want to modify only 2 or 3 parameters of a generic model for the instance we are interested in. So the script basically works in this way. It captures the output voltage of the new model nodes, and then it processes this into automatic alter statement for every defined instance in the circuit. And this is what we have here. In this case, this is ADS format, but we can also use the script to output Spectre specific format. And that's basically modifications of 3 parameters for each instance of the transistors. And this is gathered in a file, which we can simply add to the simulation later on by an include statement. So that's fairly easy. Let's go to slide 21. So now we are on step 2. We have run the initial aging simulations. We have obtained the aging results, and we have gathered all this information into an include file. So now what can we do? Clearly what we can do now is that we can any steady state simulations with the simulator with the individual aging properties for each transistor instance of the studied circuit. So what we mean by steady state simulations are AC simulations. It can be S parameter simulations. It can be harmonic balance simulations. As far as you don't have any large signal transients adding new degradation, you can run the simulation and get the properties of the circuit for a given aging condition. So in our case, this was done in command line mode by just adding the line below to the netlist, which is the include statement, containing all the alter statements that we need. And here on the graph, you have an example of AC simulations from which we can obtain the S parameters for 2 different flavors of transimpedance amplifier, one with high gain and one with larger bandwidth. And you can run these simulations in the initial conditions, that means with no stress, and you can run the simulations after 1,000 hours of accelerated aging, for instance, and see the difference. So this is practically exactly the result that we wanted to have in the end. So the conclusion is that dynamic aging models are required for circuit operating in switching mode or in large signal mode, but the practical implementation shown here would be identical for a static aging model. The requirements are: we need a specific model with integrated aging law, and we need specific output nodes whose voltage are proportional to the degradation. The simulation flow is preserved. We only change the reference to the used model library. And the methodology allows us to do 2 different things. The first one is to calculate the initial degradation for a given circuit, and the second one is to run subsequent simulations with aged circuit properties. So the proof of concept has been demonstrated here, and it has been demonstrated with a command line operation, but as you can imagine, it can be easily extended to the Cadence graphical interface because there is basically no blocking point here. That's it. I would like to thanks the French National Agency for Research, since this work was part of the Robust project. And thank you for your attention. And you have a bunch of references here on slide 24. Yeah, if you want to get more details on that. Thank you very much. Bye-bye.